So, if you were to somehow dissolve every single organ, muscle, and nerve in your body, you wouldn't just disappear.
Right, you'd leave behind this perfect ghost-like scaffolding of your entire physical self.
Exactly. It's a fascinating image, and it perfectly sets up our mission for today's deep dive. We are taking a massive stack of sources anatomy texts, historical papers, cutting-edge endocrine research to explore that very ghost, connective tissue.
Yeah, which is widely treated as just, the body's passive filler, like biological packaging peanuts meant to keep your vital organs from bumping into each other.
I mean, that's what I always thought it was.
Hmm.
But by the end of this deep dive, we are going to look at the evidence proving this is actually the most dynamic, physiologically diverse, and arguably the most important tissue category in the human body.
It is entirely foundational. And for you listening, whether you're trying to optimize recovery from a sports injury or, reading up on the latest osteoporosis
Literally
research.
following the massive cultural shift around GLP-1 weight loss drugs, right?
Sure. Yes, exactly. In all those cases, you are fundamentally thinking about connective tissue. Our sources today cover a massive spectrum to illustrate this, spanning from 18th century French dissections all the way to modern space exploration.
And the physiological hurdles of getting humans to Mars, which is just wild. We are going to ask you to completely rethink what bones, fat, and blood actually have in common.
Because on paper, putting those three in the same category sounds like a punchline to a terrible biology joke.
Right. I mean, they share seemingly nothing in terms of texture or obvious function.
No, they really don't. So to understand why this tissue category is so bizarrely diverse, we have to look at the rule that defines it. Unlike epithelial, muscle, or nervous tissue, where the cells are packed tightly together.
Like bricks in a wall.
Exactly. Unlike those, connective tissue is defined by what exists outside the cells. It is a tissue of isolation.
Okay, a tissue of isolation.
Yeah, so you have a relatively small number of cells scattered throughout an abundant extracellular matrix, or ECM.
Right, so the cells are essentially the architects, and the extracellular matrix is the building project they secrete around themselves. The sources break this matrix down into fibers, so like collagen or elastin, and ground substance.
Which is a great name.
It really sounds like a generic term for something you'd buy in bulk at a hardware store, honestly.
It does, yeah. The terminology is definitely dry, but the mechanism is brilliant. That ground substance is this complex mixture of water, proteins, and carbohydrates.
Specifically glycosaminoglycans, right?
Yes, exactly. And they fill the spaces between the fibers. By altering the ratio and chemical makeup of the cells, the fibers, and that ground substance, the body generates a staggering variety of materials.
So it's all just variations of a recipe.
Precisely.
Right.
A high ratio of fluid ground substance with loosely arranged fibers gives you loose connective tissue, that flexible packing material under the skin.
But then you stiffen the matrix with specific glycoproteins, and you get rubber-like cartilage. Or
Yeah.
mineralize it with calcium phosphate crystals, and you create rock-hard bone.
Right. It's incredibly versatile.
Okay, let's unpack this. Because laying out that recipe brings us to the biggest fault line in the sources. The most controversial member of the connective tissue family, which is blood.
Ah, yes. Blood.
I mean, it fits the technical criteria, right? It has cells, and they are suspended in a fluid extracellular matrix called plasma. But I have to push back on the terminology
I
here.
don't know where you're going with this.
Well, the German root word for connective tissue, popularized by early histologists, is Bandegewebe, literally binding tissue.
Right.
Mechanically speaking, blood flows. It doesn't contain fibers unless it is actively undergoing a clotting cascade, and it certainly doesn't bind or connect any two structures together.
The mechanical argument is exactly why blood is the subject of an ongoing pedagogical debate. Some anatomy programs teach it unapologetically as connective tissue, based purely on its embryonic origin, and that's cells within a matrix definition.
Yeah, and others don't, right?
Exactly. Others split it off into a specialized fourth subtype like fluid connective tissue because it totally strains the mechanical intent of the word connective.
Classifying it mechanically feels like looking at a river and trying to categorize it as a bridge, just because they both get you across a valley.
That's a really good analogy. But if we shift from a mechanical perspective to a functional one, classifying blood this way highlights a crucial theme. Connective tissue is hyperactive.
So it's not a physical connection, it's
a metabolic one. Blood's connection is the metabolic highway of the body. It is the moment-to-moment transport of oxygen, nutrients, hormones, and waste products.
connecting the lungs to the tissues, the endocrine glands to their target organs.
Yes. It is a chemical connection rather than a static physical rope.
Which raises an interesting historical question for me. If the definition relies on analyzing the extracellular matrix and finding shared embryonic origins, how did anatomists group something like bone and blood together before they had modern lab equipment?
Oh, that origin story is fascinating. It takes us to 18th century France with Marie-François Xavier Bichat.
Right, the guy who founded histology.
Yeah, he is widely credited with founding histology, the study of tissues, before the word itself was even coined. In 1800, he proposed that the human body was built from roughly 21 distinct tissue types.
And the sources highlight a pretty staggering detail about his methodology, which is that he categorized these tissues primarily with his naked eye.
Completely naked eye.
He subjected the tissues to desiccation, maceration, and putrefaction to observe their textures and how they degraded. He actually distrusted microscopes, arguing that they distorted reality.
Well, we have to remember the context there. Early 19th century microscopes suffered from severe chromatic aberration.
Meaning they were basically useless.
Basically, they produced these blurry, rainbow-fringed images that often created optical illusions. So Bichat relied on gross dissection and macroscopic observations of how different areas responded to disease.
And he was intense about it.
His dedication was total, and tragically, he died at age 30 from repeated infections contracted during those very dissections. Yeah. But he gave us the broad, imprecise category of cellular tissue, based simply on fibrous macroscopic textures.
It is analogous to sorting a massive bin of Lego bricks purely by color in a dimly lit room. You just lump all the red bricks into one pile based on how they look from a distance.
Exactly. But then the 1830s arrive with the achromatic microscope revolution.
The lenses are corrected, the lights get turned on in that dimly lit room, and anatomists can finally see the exact chemical polymer structure of those individual bricks.
And that technological leap paved the way for cell theory, formalized by Matthias Schleiden and Theodor Schwann, which eventually culminated in Rudolf Virchow's 1858 lecture series, Cellular Pathology.
Which changed everything.
It did. Virchow shifted the entire medical paradigm by arguing that disease originates at the cellular level. Tissues that Bichat had lumped together based on macroscopic texture were reevaluated based on their microscopic cellular matrix.
Yet, despite the scrutiny of the microscope, structures as different as tendon, bone, and blood remain grouped together because they share an underlying embryological root, right?
Yes. Almost all connective tissue traces back to mesenchyme.
Okay, let's talk about mesenchyme.
Aside from some specific tissues in the head and face that are derived from neural crest cells, connective tissue originates from this unspecialized embryonic tissue within the mesoderm. Mesenchyme is the ultimate biological starting line.
So it's basically the stem tissue.
Exactly. Those early star-shaped mesenchymal cells have the pluripotent capacity to differentiate into osteoblasts for bone, chondroblasts for cartilage, adipocytes for fat, or hematopoietic stem cells for blood.
Okay, so having established that microscopic recipe and shared origin, the sources dive into what this matrix accomplishes when pushed to its mechanical extremes.
Right. And dense, regular connective tissue is a perfect starting point.
Specifically, the Achilles tendon.
Tendons are fascinating because their extracellular matrix is engineered purely for tensile strength along a single axis. They consist of tightly packed, parallel bundles of type I collagen fibers.
The biomechanical data in the sources on the Achilles is remarkable. Using implanted force transducers, researchers measured the forces passing through the tendon during the push-off phase of a running stride.
The numbers are insane.
They really are. Those forces routinely reach 6 to 8 times the runner's total body weight. All of that kinetic energy is transmitted through a tissue rope, roughly the width of a human thumb.
And that immense strength comes down to the microscopic architecture. Those collagen fibers actually have a natural crimp or wave to them at rest.
Like a spring.
Yeah, exactly like a spring. When the load is applied, the crimp straightens out first, acting as a microscopic shock absorber before the main tensile strength of the collagen takes the full brunt of the force. It is an evolutionary engineering marvel.
So tendons demonstrate extreme static strength. But to see extreme dynamism, we look at bone. The common everyday misconception is that the skeleton is static scaffolding.
Right, people think you hit your mid-20s, your growth plates fuse, and your bones are locked in as inert calcium pillars for the rest of your life.
But bone is actually one of the most metabolically active tissues we possess.
Oh, absolutely. It is locked in an endless cycle of remodeling driven by two opposing cells. You have osteoblasts, which synthesize new bone matrix, and osteoclasts, which dissolve old bone matrix.
And the turnover rate is wild. The adult skeleton fully replaces itself roughly every 10 years, with the spongy trabecular bone turning over even faster than the dense cortical bone.
It's constantly rebuilding itself.
I have to ask about the mechanics of that, though. If bone is a rock-hard, mineralized matrix, how does it remodel its own structural integrity without failing? I mean, it sounds like trying to remodel the load-bearing walls of a brick house while you are currently living inside it.
If we connect this to the bigger picture, it all happens through microscopic coordinated units called cutting cones.
Cutting cones.
Yes, an osteoclast essentially acts as a drill bit, burrowing a microscopic tunnel through the solid bone matrix by secreting acid and enzymes.
Okay, so it's literally dissolving the bone away.
Exactly. And closely following behind that drill bit are the osteoblasts, which lay down concentric layers of new, flexible osteoid tissue that eventually mineralizes. The house doesn't collapse because this process is happening in tiny, staggered, microscopic columns scattered throughout the bone, rather than all at once.
And those cutting cones are guided by mechanical stress, right? The bone rebuilds itself along the lines of the forces it experiences.
Yes, which explains the massive hurdle NASA faces with microgravity.
Right. Mechanotransduction is the key.
Mm.
Without the constant mechanical stress of Earth's gravity, the signaling pathways shift.
The bone-dissolving osteoclasts outpace the bone-building osteoblasts. Astronauts experience a loss of 1 to 2% of their weight-bearing bone density per month in orbit.
That is just terrifying. That is a rate of deterioration that would take a postmenopausal woman on Earth an entire year to experience.
Yeah, the dynamism of connective tissue is the literal limiting factor for long-term missions to Mars.
Seeing bone as a highly active, metabolically demanding tissue transitions us perfectly into the biggest paradigm shift highlighted in our sources.
Oh, the reclassification of the ultimate biological filler tissue.
Yes, adipose tissue, fat. For most of modern medical history, fat was considered nothing more than passive energy storage and thermal insulation.
Just biological bubble wrap.
Exactly. Then we get to 1994, and Jeffrey Friedman's laboratory at Rockefeller University completely upends the field. They were studying a specific strain of obese mice, the OBOB mouse, trying to isolate the gene responsible for their unregulated appetite.
What's fascinating here is the mechanism they uncovered. They discovered that adipocytes' fat cells are actively secreting a hormone called leptin.
So they aren't just sitting there holding fat.
Not at all. Leptin enters the bloodstream and travels directly to the hypothalamus in the brain. Its job is to signal satiety, providing a negative feedback loop that tells the central nervous system the body has enough energy stores and can stop eating.
So the moment leptin was isolated, adipose tissue was instantly reclassified from passive packaging to an active endocrine organ.
Right. It is actively communicating with the brain to regulate systemic metabolism.
And this mechanism is highly relevant today. If you follow the financial or medical news, you are seeing endless coverage of GLP-1 receptor agonists like semaglutide used for weight management.
They're everywhere.
They really are. And these drugs operate in the exact downstream biological neighborhood of appetite regulation that leptin research first mapped out.
And, the endocrine function of connective tissue extends back to bone as well. Osteoblasts secrete osteocalcin, which is a hormone that acts on the pancreas to influence insulin secretion and sensitivity.
So the idea of connective tissue as inert filler is dead, completely dead. It is actively monitoring and managing our systemic energy balance.
But because connective tissue is tasked with both extreme structural loads and complex metabolic signaling, the vulnerabilities are severe.
Yeah, what happens when the matrix itself is fundamentally flawed?
Well, the clinical reality of cartilage provides a perfect example of a design flaw. Specifically, hyaline cartilage, which covers the articular surfaces of our joints. It's avascular.
Meaning it has no vascular network of its own. It relies entirely on diffusion from the surrounding synovial fluid to get oxygen and nutrients to the chondrocytes trapped inside the matrix.
Right, and because that diffusion is slow and limited, cartilage heals exceptionally poorly.
Unlike bone.
Exactly. When bone breaks, its rich vascular supply delivers a massive influx of immune cells and remodeling tools to the fracture site. When cartilage tears like a meniscus injury or damage to the articular surface, it lacks that delivery system.
So the damage just accumulates.
Yeah, it often simply accumulates, progressing into osteoarthritis.
Evolutionarily, that seems like a glaring oversight. If the lack of blood vessels guarantees the tissue will eventually fail under wear and tear, why hasn't evolution adapted to vascularized joint cartilage?
It comes down to a strict biomechanical trade-off. Cartilage sits in high-impact zones bearing the crushing compressive forces of human locomotion.
Oh, I see.
Yeah, if delicate capillaries and venules were threaded through the articular cartilage of your knee, the sheer pressure of a single jump would crush and obliterate them.
Causing massive internal bleeding inside the joint castle.
Exactly. The tissue remains avascular, so it can withstand compression, but pays the price with an inability to mount a vascular healing response.
Surgeons have been fighting that limitation for decades. The sources point to a landmark 1994 study in the New England Journal of Medicine by Mats Brittberg as a major turning point.
The autologous chondrocyte implantation study.
Yes, he developed this method of extracting a small sample of a patient's healthy cartilage, multiplying the cells in a laboratory, and then surgically implanting them back into the damaged joint to manually bypass the lack of natural cellular regeneration.
It remains a challenging frontier in orthopedics, to say the least. But mechanical injuries are only one side of the coin. The systemic nature of connective tissue becomes truly apparent when we look at genetic mutations affecting the extracellular proteins themselves.
And Marfan syndrome is a prime example in the sources. It is caused by a mutation in the FBN1 gene, which is responsible for producing the protein fibrillin-1.
Right, and fibrillin-1 molecules assemble into microfibrils, which act as a crucial scaffold for elastic fibers throughout the body.
So when that scaffold is defective, any tissue relying on elasticity is compromised.
Exactly. You see hypermobility in the joints and skeletal abnormalities, but the lethal vulnerability lies in the cardiovascular system, specifically the aorta.
Because the aorta is the massive artery exiting the heart, taking the direct, violent pressure of every single ventricular contraction.
Right. It relies on high concentrations of elastic connective tissue to expand and absorb that systolic pressure and then recoil to push the blood forward.
Without a structurally sound fibrillin-1 scaffold, the aortic wall cannot handle the repetitive stress. Over time, the vessel wall weakens and dilates, eventually leading to an aortic aneurysm or a catastrophic dissection and rupture.
And the sources reference the tragic case of Flo Hyman.
Right. The incredibly talented American Olympic volleyball player. She collapsed during a match in 1986 and died from an aortic rupture caused by undiagnosed Marfan syndrome.
It profoundly shifted sports medicine protocols, emphasizing the need to screen tall, long-limbed athletes for connective tissue disorders.
The organs themselves, the heart, the lungs, might be perfectly healthy, but if the extracellular matrix holding the system together is defective, the entire organism is at risk.
We see similar systemic cascades with Ehlers-Danlos syndrome, where mutations disrupt the synthesis of collagen, leading to fragile tissues and extreme joint hypermobility.
Okay, let's unpack this. So what does this all mean? We started this deep dive looking at a ghost-like scaffolding, challenging the idea that everything outside the major organs is just packing peanuts.
Right, and instead we found 5 liters of active blood-transporting nutrients, classified right alongside a skeleton that completely replaces itself every decade through microscopic cutting cones.
We looked at tendons handling 8 times our body weight, and adipose tissue actively secreting hormones to the hypothalamus to govern our appetite. Connective tissue isn't just the framework.
It is the structural engineering and the metabolic communication network operating behind the scenes of every biological process.
It really is.
I want to leave you with a final thought to consider, drawing on a subtle connection from the sources regarding the immune system. We discussed the cells native to connective tissue, like osteoblasts and adipocytes, but the extracellular matrix is also populated by transient and resident immune cells.
Like macrophages, mast cells, and plasma cells.
Exactly. They are embedded within the ground substance. Because connective tissue surrounds every organ, lines every blood vessel, and sits directly beneath the skin, it is the first internal environment any pathogen encounters if it breaches the body's outer defenses.
So it's basically the front line.
Yes. If this ubiquitous scaffolding is packed with macrophages waiting to engulf bacteria and mast cells ready to trigger inflammation, we shouldn't just view connective tissue as a framework or an endocrine organ. We should view it as the body's largest, most widespread immune battleground.
An armed defensive grid lying in wait, just under the surface.
Exactly.
The structural scaffolding is actually an active minefield for pathogens that completely shifts how you view your own anatomy. Thank you for joining us on this deep dive. Keep questioning the physical world around you, and the next time you think about your biology, remember that you are looking at an absolute masterpiece of mesenchyme. We will catch you next time.